Good morning to all. Myself K.S. Mohan Kumar, Assistant Professor, Erode Engineering College. I am going to give you a lecture in the subject of Communication Engineering. Today we are going to see the basic topics of Communication Engineering. This is the detection under AWGN. We can transmit the signal from the whatever it may be. The signal we can transmit through the transmitter and add the additive Gaussian noise to that signal. Then it will send to the sampler at TO0. It will rectify the problems of noise from the signal and it send to the signal to the detector. Finally, we get the output of the same what we are sending the in the transmitter. We get the output in the receiver. Here is the AWGN explanation. Additive white Gaussian noise is the AWGN explanation. Thermal noise is described by a zero mean Gaussian random process n of t that ADDS onto the signal is called as additive. It is a PSD is flat. The PSD means probability density function. That yes, probability density function. That means the Gaussian. That Gaussian is random process. Here we can explain the PSD is a power spectral density. The power spectral density is flat, hence it is called as a white signal. That means white noise. Autocorrelation is a spike at a zero, uncorrelated at any non-zero lag. So P of n equal to 1 by sigma root of 2 pi exponential of minus n square divided by 2 sigma square. This is the probability density function for the PSD. G of n of f equal to n naught divided by 2. Autocorrelation function is R of n of dou equal to n naught divided by 2 sigma of dou. This is the effective of noise in signal spaces. The cloud falls of exponential Gaussian. A vector view can be used in the signal space with the random noise vector. For the noise cloud, we can use it. Smudge space is the noise cloud. We can effectively using a Gaussian. That means AWGN. We can use it here. We can clearly observe the vector, received point signal, noise vector, message point, signal vector. All the outputs are we will get the same process. Maximum likelihood ML detection. That means for the scalar cases, the maximum peak point is a likelihood. So here we can get P of U equal to UA divided by UA of Y is greater than or equal to P of U equal to UP of Y. This is the sample distance criterion. Log likelihood is equal to Y of minus UA is a model is less than model of Y of minus UB. This is the maximum likelihood detection. So AWGN detection for binary PAM. For the high peak, we get an detection of binary PAM. Y is similar to n of UI, comma n naught divided by 2. This is the maximum of power using for the AW detection for the binary. So finally we get an PB is equal to P of 2 equal to Q of root of 2EB divided by n naught. This is the maximum binary value for the binary PAM of AWGN. So this is the basic picture for the communication system. First we transmit the signal from the source to the transmitter. Here transmitter block have a 4 blocks: formatter, source encoder, channel encoder, modulator. These are the 4 blocks used in the transmitter. This transmitted signal again passed through the channel. That channel have a noise. That noise is useful to reduce the noises or a reduction for the any particular noises. That signal is again transmitted to the receiver. Receiver have a same 4 blocks, but here is the receiver have a some different blocks. That means transmitter have an encoder, receiver have a decoder. So formatter, source decoder, channel decoder, and demodulator. This block is transmit the information to the user. So finally we will get the communication system output from this basic form of the block diagram. Digital vision analog communication basics. First, digital versions analog. Advantage of digital communication is generator, receiver. Whatever the signal is generator, the same signal is we get the same signal on the receiver side also. This is the basic advantages of digital. So different kinds of digital signals are we are using. For example, we can use WhatsApp for the data communications, or voice communications, or media communication. A bit is a bit, so we can use that communications through whatever it may be. It is a data, or it's a voice, it's a media, whatever it may be. We can transfer the data to the WhatsApp from bit. From a bit is a bit. Signal transmission through linear systems. For the input sections, we can give an x of t and x of f. This signal is transmitted to the linear system. For the linear system, h of t and h of f. So these two are combined to get the output of y of t and y of f. So for the deterministic signal, y of f equal to x of f into h of f. For the random signals, we get gy of f is equal to gx of f, a model of h of f the whole square. Here the model f of the whole square is a formation of all the noises, and whatever it may be, AWGN is the formation of h of f the whole square. The ideal distortionless transmission is all the frequency component of the signals not only arrive with an ideal time delay, but also are amplified or attenuated equally. Y of t equal to k of x of t minus t naught, or h of f equal to k e power minus j 2 pi f t naught. This is the basic ideal transmission, less for the transmission. Here the signal transmission, the same signal transmission is using for the three passes. First one is low pass, second one is band pass, third one is high pass. For the low pass transmission, this is the casually using for all the signals. We can get it signal from the low one to high signal. Here we are using the signals of sine signals, are using for the transmitting of the signals. For the band pass, we can use filters, uh, RC filter and Butterworth filter. These two filters are using for the band pass filter and a high pass filter. For the filters, h of f equal to this filter is using for the RC filters. H of f is equal to 1 divided by 1 plus j 2 pi FRC. So finally we get an output of RC filter. Butterworth filter is an model of Hn of f equal to 1 divided by root of 1 plus f divided by fu the whole power 2n. This is the basic Butterworth filter formula. These formulas are using for the finding the Butterworth filters and the RC filters to hit the high pass or band pass, whatever it may be. We just need to find the filters. So band signal of signals. Here we are using the baseband versus band passes. Here we are using the baseband signal to the local oscillator. Local oscillator means we can using a some other additional signals to the signals. Finally we get an band pass signals. For example, x of t is passing through cos of 2 pi fct, then we get xc of t. That means band pass signal equal to x of t cos of 2 pi fct. So this is the final formula for the output region. So bandwidth dilemma, that means band limited signals are not realizable. Here the band limited signals are not realizable. Realizable signals have a infinite bandwidth. That means, so bandwidth is not absolutely we cannot find for the signals. So band signals of approximations. So totally 6 band signals are using. So first is the absolute bandwidth. That means it's a flat bandwidth. We get this bandwidth from the total output signals. Next one is half power bandwidth. Half power bandwidth is a small bandwidth. We can get only the half power of the bandwidth. Next one, noise equivalent bandwidth. Noise equivalent bandwidth is an more than half power bandwidth. That means it is not equal to half power bandwidth, but it is higher than half power bandwidth. Next one is null to null bandwidth. Null to null bandwidth is a higher bandwidth comparing to the half power bandwidth and the noise equivalent bandwidth. The fourth one is fractional power containment bandwidth. This bandwidth is used for an fractional power. That means this power is used to exactly getting the output for the fractional values. And this bandwidth is not equal to half power and also noise equivalent and also null to null bandwidth. But it is more than these three bandwidths. Next one is bounded power spectral density. This bounded power spectral density is the highest power spectral density when we comparing for the bandwidth of the signals. This bandwidth is more useful for the finding the output of the exact signals. So this bandwidth is an exactly using for the uh, output. This bandwidth have a particularly 50 dB has a output. This is the formatting for um, baseband signals and the transmission of baseband signals. So here the source is digital information, textual information, analog information, whatever it may be. Previously we discussed this. So for the digital information, we can type a text. Sorry, we can give an image or video, voice, whatever it may be. For textual information, we can give a text database like that. Analog information is we can give a voice message, whatever it may be. We can send the sources to the sample theorem. Again, that sample theorem will convert the signals into the quantization process. That quantization will process will again send the signal to the encoder. So these encoder will give a bit stream to the pulse modulator signal. That pulse modulator signal will transmit the our signals to the channel. That channel, if the noise is occurs, if the some other output noises are occurring there, it will reduce the noises and then send it to the receiver. This receiver part will be demodulated and detector the signals, and finally we can get a decoder with the low pass filters. This is the process of the formatting and the transmission of the band signals. So these can be useful to transmitting the signal and receiving the signal from the our sides. This is a sampling of analog signals. We can comparing with the time domain and frequency domain. For the time domain, xs of t equal to xs of t into x of t. And, for the frequency domain, xs of f equal to x of f into x of f. For the time domain, we can exactly calculate the timing of 0 to 1, 0 to 2, 3, whatever the peak values of the signals, and what is the negative values of the signals, we can identify it in time domain. For the frequency domain, which frequency it will occur, which what is the frequency is necessary for the occurring of the signals, this can be found in the frequency domain. Aliasing effect and Nyquist rate. Aliasing effect is the effect which is used to identify the error occur or noise occur in the particular signal is called aliasing effect. Nyquist rate is a rate which will gives the more than power of low pass filters. That is called as a Nyquist rate. Here the diagrams will explain the clarity of the Nyquist rate and also aliasing. For the Nyquist rate, we can use in a low pass filters. That low pass filter f is equal to 2fm. For the aliasing effect, we can use the fs is less than 2fm. That means aliasing effect. Undersampling and aliasing in time domain. For the undersampling and aliasing in time domain, we can use a high frequency signal sampled at a low order rate. Finally, it looks like a lower frequency signal. So we just need a lower frequency signals to find the output of the uh, aliasing in time domain. So we can exactly get the whatever we need. That output will we get it. Okay, this is the Nyquist sampling and reconstruction domain. Students, here we using a high frequency signal and added the sample fast enough may still look wrong. So finally we can get the reconstructed output for the particular Nyquist and time domain. The here you can note correct reconstruction does not draw a straight line between the samples because it is a synchronizing pulses for the reconstruction and interpolation. So that's we using the method to find the Nyquist sampling and reconstruction time domain. Okay, here the Nyquist reconstruction frequency domain. So for the Nyquist reconstruction, a sampled signal must be a low pass filter to reconstruct the originals. The impulse response of the reconstruction filter has a classic sine x of x shape. The stimulus feed to this filter is a series of discrete impulses which are the samples. So finally we get an Nyquist reconstruction frequency domain to absolutely get an what is the output of up to the point of 1. The sampling theorem. Here the sampling theorem is used for the analog signals, the sampling process and the PAM pulse amplitude modulation signals. The sampling theorem is a band limited signal which has no spectral components beyond FM can be uniquely determined by values sampled at uniform intervals of T of S is less than or equal to 1 by 2 FM. For the sampling rate, Fs is equal to 1 by Ts is equal to 2 FM. This is the sampling rate for the Nyquist rate. In practice, we need to sample faster than this because receiving the filter will not be sharp. Quantization. This is the quantization process. The quantization process is the step-by-step process for the continuous amplitude waveform to a finite set of amplitude. So finally, quantize the value of the Vp to minus Vp. In averages, basically quantization noise power is a sigma square is equal to q square divided by 2, sorry 12. The signal peak power is a Vp square is equal to L square q square divided by 4. The signal power to average quantization power is S by N of q equal to Vp square divided by sigma square equal to 3L square. These are the basic quantization formula for the output. Next, encoding for the VPCN. The VPCN is a pulse code modulation. Uniform linear quantizer is called as a pulse code modulation. Here the VPCN encoding the quantizer signals into a digital words. That means PCM word or code word. Each quantizer sample is digitally encoded into n L bits. Code word number L is the number of quantization levels and L equal to log to L. So quantization error. Quantization error is the difference between the input and the output of the quantizer. That means E of t equal to x cap of t minus x of t. The process of quantization is first we can give AGC to the input signal of x of t. Finally, we get the output of x E of t is equal to x cap of t minus x of t. For the quantization, it is a step-by-step process. So y equal to q of x. For the model of quantization noise, we have x of t is an adding a summarization of E of t q into the x cap of t. So non-uniform quantization process. For this non-uniform quantization process, it is done by uniformly quantizing the compressed signal at the receiver. An inverse compression characteristics called expansion is employed to avoid a signal distortion. That means compression plus expansion is equal to compounding. So here we can give an output of compression and quantization also gives us a transmitter. Finally, it will get sent to the channel. The channel will give the output to the receiver side. This will be the expansion of the receiver. So finally, we can get a channel with transmitter signal with the noise of output signal. We can give as an output signal. So baseband transmission, to transmit information through physical channels, PCM sequence are transformed to pulses uniformly. For each waveform carries a symbol from a set of size m. Each transmit symbol represents k equal to log to m, the bits of PCM words. The PCM waveforms are used for carry symbols, binary symbols m equal to 2. M array pulses modulations are used for a non-binary symbols m is greater than to example M array PAM. For giving a data rate M array PAM, that means M of M is greater than 2 requires less bandwidth than the binary PCM. For a given average pulse power, binary PCM is easier to detect a M array PAM. M array is greater than 2. For the PAM signals, binary is as 8 array. Here we can see the students for the first diagram is an 8 array PAM, second one is binary PAM. For the 8 array PAM, we can consider as an positive signals for the sloping of the output. For the binary PAM, we cannot consider which one is positive, which one is negative. We can calculate all the negative and positive pulses with the final output. Examples of M array PAM, assuming real time T of x. Here we are using 4 array and binary array. So here for binary PAM have a rectangular pulses, that means zeros and ones. For 4 array PAM, rectangular pulses have a 0, 1, 10 and 11. Other PCM waveforms examples. Here we have other form of PCM waveforms categorized: non-return to zero, return to zero, phase encoder, multi-level binary. These are the 4 steps we have followed in the other PCM waveforms. PCM waveform selection criteria. For the selecting the PCM waveform criteria, we have certain criteria to selecting the PCM waveform. Criteria for comparing selecting PCM waveforms: spectral characteristics, bit synchronization capability, error detection capability, interface and noise immunity. Last one is implementation cost and complexity. Summary of baseband formatting and transmission. This is the basic summary. First, we can use already we discussed this in the previous classes. For the sources, digital info, textual info, analog info. These are the 3 basic informations. We can just pass this information to the sample. That sampling at rate fs equal to 1 by ts. This is the sampling time ts. Then again, the sampling rate will be passed to the quantization process. This is quantization. Each sampled value to the one of the L levels is quantized. Again, it will send it to the encoder process. That encoding process will be encoding each q value to the L equal to log 2 L bits. Data bit duration TB equal to TS divided by L. Finally, it will send the output signal to the pulse modulator. That pulse modulator will be mapping every M equal to log 2 M data bits to a sample out of M symbols and transmitting a baseband waveform with duration T. Finally, the pulse waveform baseband signals we can get the output of the transmitter signal. For the information, data or bit, it will be rated as RB equal to 1 divided by TB bits per second. For the sample rate, R equal to 1 divided by T. That will be the uh, symbols divided by second. Finally, RB equal to MR. This is the before the slides we can discussing about the transmitter. Now we are going to discussing about the receiver structures and matched filters. So demodulation and detections. For the demodulation and some detections, formats we are using for MI, pulse modulator, band pass modulator. Again, it will send it to the channel and then added to the demodulator at sample and detector and the formatted. MI is a transmitted symbol. MI is MI cap is an estimated symbol. Finally, we can get MRA modulation I equal to 1 to M. Major sources of error: thermal noise. For the thermal noise, AWGN disturb the signal in an additive fashion. That means additive has a flat spectral density for all frequency of interest. That means white is modeled by Gaussian random process. It's a Gaussian noise. Intersymbol interference is the ISI due to the filtering effect of transmitter channel receiver symbols are memored. Impact of AWGN, that means the level of the impact of the AWGN. Using this formula we can using the waveform for the correctly we can get the impact. The impact of AWGN and channel distortion, HC of T equal to sigma of HT 0.5 omega of T minus 0.7 T. Receiver's job. For the receiver's job, demodulation, undersampling, waveform recovery, and preparing the received signal for the detection, improving the signal power to the noise power SNR, using the matched filter, project to the signal spaces, reducing ISI, using equalizer, remove the channel distortion, sampling the recovered waveform. Detection. What is the detection for the receiver's job is estimated the transmitted symbol based on the received sample. This is the receiver structure for the output. Finally, we can give the input to the received waveform. It will send it to the frequency down conversion for baseband signals. Again, it will send it to the receiving filter. That output is considered as a baseband pulse, possibly distorted, to the equalizing filter. That output will be used as a baseband pulses, and that opening circuits will give you the output to the sampling test statistics. These outputs are passed through the decision making block, that is a step 2. Here we can detect threshold comparison. Finally, we can get an MI of the output. Baseband and passband versus, what is the comparison of baseband and passband? For the band pass, we can use model of detection process is equivalent to the baseband model because the received baseband waveform is first transformed to a baseband waveform. And next one is equivalence theorem. What is the equivalence theorem? Means performing baseband linear signal processing followed by a heterodyne the signal to the baseband. Then again it sends to the processing to the yields the same result as heterodyne the bandpass signal to the baseband followed by a baseband linear signal processing. Next one is steps in designing the receiver. Find optimum solution for receiving design with the following goals: maximize SNR, that means matched filter, minimize ISI, that is an equalizer. So steps in designing, what are the steps to follow for designing the receivers? Model the received signal, find separate solution for each of the goal. First we focus on designing a receiver which maximize the SNR, that means matched filter. Receiver filter to maximize the SNR. Model the received signal. SI of T equal to HC of T. That means N of T, AWGN. Before the first class, we are saying that AWGN. So the signal is adding in the comparator. Finally, we can get an R of T. R of T equal to SI of T into HC of T plus N of T. Simplify the model. That means ideal channel assumption. Here is the received signal in AWGN. Ideal channels is HC of T is equal to sigma of T, Si of T is equal to added in N of T AWGN. Finally, we get an output of R of T. So R of T equal to Si of T plus N of T. Here is the problem to solve it for the evening. So we can solve these problems using matched filter receivers. The problem is design the receiver filter h of t such that SNR is maximized at the sampling time when Si of t is equal to I equal to 1 etc. up to m is transmitted. Kindly using the SNR formula to apply this receiver filter h of t, finally find the h of t order output. Correlator receiver. For the correlator receiver, correlation process is the projection of the received signal onto the signal space. This is the recall for the correlation. Here we can use the key idea, reject the noise outside the space as irrelevant maximum S by n. Matched the filter output at the sampling rate time can be realized as the correlator output. Matching filtering, that means convolution with Si into t minus dou simplifies to integration W of Si into dou, that means correlation or inner product. Z of t equal to H opposite of t into R of t, 0 to t. It's an integral 0 to t R of dou Si into dou d dou is equal to less than R of t comma S of t. Irrelevance theorem, noise outside signal space. Noise PST is flat, white is equal to total noise power, infinite across the spectrum. We care only about the noise projected in the finite signal dimensions, that means bandwidth of interest. So aside correlation effect, if two signals are similar and unshifted, the product is all positive, but as the shift increases, part of it becomes negative, and the correlation function shows where the signals are similar and unshifted. The correlation is maximum when two signals are similar in space and are in phase. The correlation is measure of the similarity between the two signals as a function of time shift. When the two signals are similar in space and unshifted with respect to each other, their product is all positive. This is like constructive interference. The breadth of the correlation function, where it has a significant value, shows for how long the signal remains similar. Assigned autocorrelation. For the assigned autocorrelation, randomizer is similar to itself and in phase only with no time shift at all. So it is correlation function is a spike. Periodic signals go in and out of space as they are time shifted. So their correlation function are periodic. Signals that last only a short while are only similar while they last. So their correlation functions are short. Aside across correlation and radar. For the radar or sonar strip signal, bounced off a target may be buried in a noises, but correlation with the strip reference clearly reveals when the echo comes. For this, radar is used for the satellite or a helicopter, aeroplane, whatever it may be. We can communicate with the higher end of the peoples who are all above the skies. We can use this radar signal to communicate with the peoples. A copy of the known reference signal is correlated with the unknown signal. The correlation will be high when the reference is similar to the unknown signal. The large value for the correlation shows the degree of confidence that the reference signal is detected. The large value of the correlation indicates the reference signal occurs. This is a chirp of a nightingale. That means the voice of the nightingale will be accurately recorded as this. The correlate is strongly with another nightingale, but weakly with a dove or weakly with a heron. So we can compare the voice signals with the three different birds. Again, it will compare with the nightingale. So for the nightingale, it gives a highest chirp of a voice. The another nightingale will not produce the highest chirp of the nightingale, but dove has a weakly voice signal. Heron has a highest voice signal. A copy of known reference signal is correlated with the unknown signal. The correlation will be high if the reference is similar to the unknown signal. The unknown signal is correlation with the number of known reference function. The large value for correlation shows the degree of similar to the reference. The largest value for the correlation is the most likely matches. The same principle in communication, reference signals corresponding to symbols. The ideal communication channel may be attended, phase shifted, the reference signal and added noises. Matched filter back to cartoon. We can use AWGN signal to the input signal. That matched filter will be used the output of 11011. This will be the considered as a digital filter. Consider the received signal as a vector R and the transmitted signal vector as a yes. Matched filter project the R onto the signal space spanned by S matches it. The filtered signal can now be safely sampled by the receiver at the correct sampling instant, resulting in a correct interpretation of the binary messages. Matched filter is a filter that maximizes the signal into a noise ratio. It can be so that it also minimizes the BR. It is a simple projection operation. Examples of matched filter. First we are using ASI, next one is HOPT, finally Y of T is the output. So we are getting an SI of T into H optimal of T. So we can use these two signals to find the output of 0 to 2T. So SI of T equal to optimum of T, A divided by root of t minus a divided by root t. This is the signals we can follow. So two signals we can follow here. So finally y of t equal to si of t into h optimization of t. Properties of the matched filters. The Fourier transform of the matched filter output with matched signal as an input is expected for a time delay factor proportional to the EST of the input signal. Here z of f is equal to modulus of s of f the whole square exponential of minus j 2 pi ft. The output signal of a matched filter is proportional to the shifted version of the autocorrelation function of the input signal to which the filter is matched. Here z of t is equal to rs of t minus capital T is gives us an z of t is equal to rs of 0 equal to es. The output SNR of a matched filter depends only on the ratio of the signal energy to the PST of the white noise at the filter input. Maximum of S divided by N of T is equal to ES divided by N naught divided by 2. Two matching condition in the matched filtering operation. Spectral space matching that gives the desired output peak at time. The spectral amplitude matching that given optimum SNR to the peak value. Implementation of a matched filter receiver. Bank of M matched filters. R of t equal to S1 of capital T minus small t, S sum of capital T minus small t. Z1 of t, Zm of t. These are the branches. Finally gives an Z matched filter output observations vector. Za is equal to R of t into Si of t minus t, I equal to 1 comma m. Z equal to Z1 of t comma Z2 of t observe etc up to Zm of t. The finally output also given as an Z1 to Z2 comma etc up to Zm. Note we are projecting along the basic directions of the signal space. So implementation of the correlator receiver. This is a bank of correlator. Finally we can get the output in the previous side. We will filter, that means convolution in the boxes. This is the implementation example of the matched filter receivers. Here we can match the filter of two matched filters we can use it here, so that output will be used as an EZ. The matched filters frequency domain view. For the frequency domain view we can get an filter accurately like this. For the simple band pass filter exclude a noise, but noise is some signal power. So matched filter frequency domain view continuously. Multi band pass filter includes more signal power but adds more noise also. Matched filter includes more signal power weighted according to the size, maximal noise rejection. So maximal ratio combining MRC viewpoint. Generalization of this F domain picture for combining multi-tap signals. Weight each branch with a complex factor Qi equal to modulus of Qi e power j pi a, and then adding up the NR branches. For SNR equal to sigma of MRC equal to, this is the final equation for the SNR. This is the samples of matched filter output for the passband modulation schemes. QPSK 8 pp, 8 psk, qpsk, 8 psk. Signal space components. This is we are going to discussing about the signal space components. The signal space overview. What is a signal space means? The vector representation of a signal in an n-dimensional orthogonal space. Why do we need a signal space? It means to convert signals to vector and vice versa. It is a means to calculate signal energy and the equivalent distance between signal. Why are we interested in an equivalent distance between the signals? For detection purpose, the received signal is transformed to a received vectors. So signal which can maximize the distance of the received signal is estimated as transmitted signal. The spectrometric signal of a signal space is signal space. To form a signal space, first we need to know the inner product between the two signals. The inner scalar product is x of t comma y of t is equal to integral of minus infinity to plus infinity x of t y of t dt. Signal space. The distance in signal space is measured by calculating the norm. What is the norm? Norm of a signal is the sample of distance in a signal space. This is the orthogonal signal space. N-dimensional orthogonal signal space is characterized by n linearly independent functions called basic function. The basic function must satisfying the orthogonality conditions. Example of an orthonormal base. Two-dimensional orthogonal signal space. The first dimension orthogonal space signal space sine or cosine basis notes as approximately orthonormal. This is the example I'm going to give you for the BPSK problems. You have to, students, you have to solve these norms. Signal space an arbitrary finite set of norms where each number of the set is of duration t can be expressed as a linear combination of n orthogonal waveform. For the signal space, waveform to vector conversion, vector to waveform conversion. Example of projecting signals to a orthonormal signal space. Matched filter receivers. The bank of n matched filters is used for n is less than or equal to m. The correlation receiver is the same signal we can receive, but n is less than or equal to m. Example of matched filter receivers using basic functions. The white noise in orthogonal space signals. For the modulation techniques, we can using for the basic formations of the modulations. Here we can discuss what is modulation. The modulation is encoding the information in manner suitable for the transmission. Translate baseband source signal to the bandpass signal. Bandpass signal is a modulator signal. How it can be modulated means vary amplitude, phase or frequency of a carrier. Demodulation. Demodulation is a extract baseband messages from carrier. Digital vision analog modulation, cheaper, faster, more efficient, high data rates, power error correction, impairment resistance, using coding, modulation, diversity, equalization, multi-carrier techniques for ISI mitigations, more efficient multi-cases strategies, better security, CDMA, encryption, etc. Goals of modulation techniques. It's a basically they have a high bit rate, high spectral efficiency, high power efficiency, low cost and low power implementation, robustness of impairments. Modulation representation. Any modulated signal can be represented at S of t is equal to a of t into cos omega c plus pi of t. This is the basic modulator signal. Finally, we can get linear versus nonlinear modulation. Impact on spectral efficiency. Linear implemented or phase. Nonlinear frequency. Spectral broadening. Constant employee versus non-constant employee versus hardware implications with impact on power efficiency. Complex vector spaces. Here we can use the MPSK model for the circular. Here we can use the QAM vector for the square. So linear modulation techniques. There are two linear modulation. First one M array quadratic and M array phase. Here M array quadratic we can use an amplitude modulation. M array phase we can use a shift keying. So MPSK and QPSK, this is the circular motion for MPSK. MQAM is a square constellations. Bandwidth versus power efficiency. MPSK, MQAM and MFSK. These are the basic functions we are using for the calculation of the bandwidth and power efficiency. PAM and symbol mapping. Note the average energy per bit is constant. Gray coding is used for mapping bits to the symbols. Why most likely error is to confuse with the neighboring symbols. Make sure that the neighboring symbols has only one bit difference. PAM details. Unequally homogized symbols. This is problems I'm going to give you for the solution of the problems in the futures. Where we can go for a mobile phone subscription worldwide. Here we can use as a GSM total, TDMA total. The black color represents GSM and rose color represents the TDMA, yellow color represents as a CDMA, and blue color represents a PDC. These are the total wires we are using the day by day. We can improve the technologies, whatever it may be. We just improve the technologies for the worldwide. This is the worldwide of mobile telecommunication system. Here using a CDMA, TDMA and FDMA. We can use as a, for the TDMA we can use GPRS, GSM, whatever it may be. Now presently we are using a TDMA for the higher frequency of the modulations. So GSM overview. GSM. What is meant by GSM? GSM is a group sample mobile founded in 1982 global function system for a mobile communication. Now we are calling as a global system for the mobile communication. This was established in Pan Europe. That means ETSI, European Telecommunication Standardization Institute, is founded this stimulate the instruction of the essential service in three phases in 1991 to 1994 and 1996 by the European Telecommunication Administration. Again, it will send to the Germany T1 and T2. Totally, many providers are all over the world using GSM. More than 184 countries in Asia, Africa, Europe, Australia, and America. More than 747 million subscribers are using GSM for their mobile phones. The performance characteristics of GSM: the communication, total mobility, worldwide connectivity, high capacity, high transmission quantities, security functions. So these are the performance of characteristics of GSM. Distance of GSM. There is no difference, perfect system because no end-to-end encryption of the user data, no full ISDM data bandwidth of 64 kbytes per second to the user, no transparent B channel, reduce concentration while driving, electromagnetic radiations, abuses of private data possibles, roaming, profile accessible, high complexity of the system, several incompatibility with the GSM standards. GSM mobile service. For the GSM mobile service, GSM offers several type of connections: voice connection, data connections, short message services, multiple services, combinations of basic services. There are three service domains: barrier service, telematic service, supplementary service. This is the basic three services for the mobile communications. First one, barrier service. Barrier service is to transfer data between the access points. Telecommunication service to transfer data to between the access points. Specification of service up to the terminal interfaces. Teleservices. Teleservices is the telecommunication service that enable voice communication via mobile phones. All the basic services have to obey cellular function, security, measurements, etc. This is telecommunication 2. This is non-voice services. Group of three factors: voice mailboxes, electronic mails are used for the teleservice 2. Here we also included the SMS. Supplementary services. Services in addition to the basic service cannot be offered standalone. Similar to ISDN service, besides lower bandwidth due to the radio link may differ between different service providers, countries, and protocol versions. Important services. Architecture of the GSM. GSM in public LAN mobile network. The several providers set up mobile networks following the GSM standard within each country. Components: mobile station, base station, MSC mobile switching center, local registration, subsystems, RSS, NSS, and OSS. These are the subsystems using for the architecture of the GSM. GSM overview. Here we can using the GSM for the function of OMC, AR, AUSC For BSC is a basic station service. We can use it for the services. This is the overview. These are the elements and interfaces for the GSM architecture. We can use the radio system, networking system, and fixed partner system. So it will be classified into three basic parts. First one is radio subsystem. Second one is network and switching subsystem. Third one is fixed partner networks. Uh, the system architecture radio system. First one is a radio subsystem, networking and switching subsystem. AMS, BTS, and BSS. These are the BSS is a base station subsystem. MS is a mobile station. BTS is a base transceiver station. BSE is a base station controller. So system architecture working and switching subnet. Network subsystem fixed partner networks ISDN, PSTN. We are using MSC. For the MSC is a mobile service switching center. IWF is an interworking functions. ISDN is an integrated service digital network. PSDN is a public switched telephone networks. PSPDN is a packet switch public data network. CSPDN is a circuit switched public data network. Databases. HRL is a home location register. VRL is a visitor location register. EAR is a equipment identifier register. Radio subsystem. Radio subsystem is shortly called as an RSS, comprise the cellular mobile network up to the switching centers. GSM cellular networks. For this use of several carrier frequency, not the same frequency in adjoining the cells. Cell sizes vary from some 100 mm up to 35 km depending on the user's identify, reprography, transceiver power, etc. Hexagonally use of cells is idealized cell overlap shapes depends on the reprography. If a mobile user changes cells, handover of the communication to the neighbor cells. Example coverage of GSM networks. This is the T-Mobile, Vodafone, E plus O2. These are the some of the networks we using these networks from gsmworld.com. This is a base transceiver stations and the base stations controller for taking the BTS and BCS. Mobile station. This is the mobile station we have used for the comparisons of MTTATE and SIM. Network and switching subsystems. NSS is the main components of the public mobile network GSM. Components we are using mobile servicing switching center is the components. Database home location register, visitor location register. Mobile Service Switching Center (MSC). The MSC is a mobile switching center, plays a central role in GSM switching functions, additional functions for mobility support management of network resources. Functions of MSCs are using in the mobile service switching centers. Operation subsystems. That means OSS enabled centralized operations. GSM, TDMA, FDMA using for the functions of the basic frequency for the mobile transmitters. GSM hierarchy of frequency. This is the GSM protocol layer for signaling. Mobile terminated call. Calling a GSM subscriber, forwarding a call to GMSC, signal call setup to HLR, request SNRN from VLR, forward responsible MSC to GMSC, forward call to current MSC, get current status of MS, packing of MS answer, security checkup, setup connections. This is a mobile oriented cells. Two connections required, 4 security checkup, 8 check resources, 10 setup calls. 4 types of handovers. Handovers is a network which will be hand over the mobile from the one places to another places. That means if you traveling in a car, means you can switch over to one places to another places. That one network to another network changing over or switching over is called an handover. This is the handover decisions. If we are traveling from MS to MS, how the signals will transmitted from the one end of the transmitter to another end of the transmitter. This is the handover procedures. First, we can traveling from one places to another places, which will be transmit automatically transfer the signal to the one pages to another pages. Security in GSM. GSM authentications. This is the basic GSM authentications mobile network using SIM for the KA RAND 2 RAND KA. It's a A3 SRES 32 bits. GSM key preparation encryption mobile network BTS MS with a SIM. Data service in GSM, data transmission standardized with only 9.6 kilobits, the high speed security switched data. Data service in GSM to GPRS, general packet radio service. GPRS is a network elements. GPRS quality of service. This is the GSM architecture and interfaces. Or GPRS protocol architecture. Directing system architecture reference model. DCT reference model. DCT layer 1. This is the physical layer, MAC layer.